Now, as I just said, we are going to devote the next hour, next class, to a review, a fast review, a quick review of the direct stiffness method. Now, the direct, sorry, until I, no. Yeah. Now, all modern implementations of the finite element method used by major commercial finite element method codes use the stiffness method. That's what I just said to you. There other possibilities have been tried, but in practice, this is the one that everyone uses. Okay? Now, the direct stiffness method, as we will see in a second, is a very democratic method in the sense that we have a very systematic procedure that works exactly the same no matter what the element we are working with. Okay? And there are a huge amount of possible elements to be used in the analysis. And we are going to use in the second hour, we are going to pass a little list of the elements. The simplest possible finite element to be used is this one. This is a linear element, a truss member with only 2 nodes at the end, and each node has only 2 degrees of freedom, 2 translations, okay, x and y. This means that we have 2 times 2, 4 degrees of freedom. But we have other members in the family of the finite element space. Elements like this. This is a tricubic brick element in 3D, so it has 8, 16, 16, 16, and 16, that's 64 nodes, and each node has 3 degrees of freedom, 3 translations, so this means that this brick has 192 degrees of freedom, okay? So rather than making an introductory class on the method based on this element, we are going to do it based on this, because it's the most trivial one, okay? You will understand directly how this element works. It's not so straightforward to know how this element works as an element. So we'll just concentrate on knowing how the element works, how do we proceed with it, okay? So here we have a sketch that we are going to repeat later on what is model-based simulation and where the finite element method fits. It fits here. So without going into many details, because if you have any questions, you can do it. Here we have a physical system. Well, the physical system is physical. There is no mathematics attached to the physical system. So the first thing we do, because of training, we build a mathematical model of the physical system. So we attach mentally mathematical quantities to physical properties and so on. This process is called idealization. So we have a mathematical model. The mathematical model does not need to be discrete, does not need to have discrete elements to be identified. It may very well be continuum. Okay? A plate, the floor, you see? The floor we are standing on, that's continuum. A dam, a bridge, the deck of a bridge. Now, we have mathematical tools to analyze this mathematical model, but they are limited. Okay? So the finite element method turns this mathematical model into a discrete model, and that process is called discretization. And then these, once discretized, we can solve, and then we have the solution. Now, the discrete solution is the discrete solution to the discrete mode. Now, if we try to insert the discrete solution into the discrete model, we measure the solution error. We usually assume that the solution error is 0, but it may not be so 0. Okay? But let's assume that this is 0 for the time being. Even if the discrete solution satisfies very well the discrete model, it is fairly obvious that it will not satisfy so well the exact mathematical model. And then the addition of this plus this difference is the discretization plus solution error. Okay? And finally, if we compare the solution of the mathematical model with the physical reality, then we are adding whatever modeling error we have introduced during the idealization. Okay? This process of trying to measure the error that we have done in the different phases of the simulation is called verification and validation. Now, let's assume that we start with a physical system which is something like this. Okay? This is the roof of something. Okay? An industrial building or whatever. Now, because of the training, particularly those of you who are civil engineers, and probably the mechanical ones as well, because of the training, because of the years you have been in the university doing this thing, the idealization of this into the mathematical problem is quite easy. You see something like this. Okay? But this is not automatic. This is because of the training you have. Obviously? See, here, well, first of all, we have decided that everything over the truss is loads. Okay? So we are automatically disregarding any structural influence of the roof itself. Okay? Why? Well, because we think it's not going to contribute. Okay? Now, we are assigning the weight of the roof to the nodes. Why? Well, because we have been trained to do so. We are assuming that these connections are not restraining the rotation. Why? Well, because we have been told that it doesn't restrain too much. Okay? And we are doing some other assumptions in the idealization. For instance, we have decided to make this point fixed and to put a roller here. Well, in the real system, these and these are exactly identical. So why are we making them different? And in particular, why are we making the mathematical model like this? Is there any other possibility? Well, there are. We are not going to spend a lot of time here, but consider this question. Why did I put my fixed point here and my roller here when in reality there is no roller here and no roller here? They are identical. Do you have an answer for that question straightforward right now? Or you have to think of it. But once this mathematical model appeared, I saw some appreciative noddings. Okay, yes, I would do this. Okay? Well, the pass from here to here is the idealization. Okay? In this particular case, the mathematical model is already discrete. Okay? It's already discrete because we can assign numbers to the members, and it is a finite number of members. They are very clearly identified. And we can assign numbers to the nodes, and they are very clearly identified as a yellow dot. In other cases, the mathematical model is continuum and still needs to be discretized. Okay? And we will consider this next. Now, this is how the direct stiffness method proceeds. In these steps, always these steps. Okay? First, we have the idealization. Okay? This is the problem. Sorry. Second, we remove the loads and the supports to be safe for later on. So we consider the structure floating in the air. This is what in our first courses we call the free body diagram. Okay? So we consider the structure floating in the air, without loads, without support, nothing. Now, we disassemble. So we disconnect all the elements from each other, just like that. Okay? And we localize, which means that we put this element here, and this element here, and this element here. Okay? And we say, we have so many diagonals, we have so many buttons, we have so many lower longerons and upper longerons. Okay? We are identifying the pieces of the structure. Okay? This is the breakdown. Now, once we have done the breakdown, we are able to consider one generic element at a time. So we take one element and we say, now, what do we do with this element? Okay? What do we do with this element? We pass to the second phase, and in the second phase, sorry, it goes too fast. In the second phase, one element by element, we form the elements. We will see in a few minutes that by forming the elements, we mean that we need to form the stiffness matrix and the force vector of the element. Okay? When we have done this, we globalize, which means that we take this element and we put it here, and we take this element and we put it here, and we take this element and we put it here. Okay? We merge. We mean that we identify that this node, and this node are all the same. We put back the loads and the supports, and we solve. Okay? So that is the steps that we always do. Okay? For any example. Now, let's give names to this. We have a breakdown, and we have the assembly and the solution. The breakdown we have called disconnection and localization, and element formation. And then the assembly and solution we have called globalization, merging, application of the boundary conditions, meaning loads and supports, and solution. By the way, the solution will give us, the displacements. But we want more than the displacement. We want, for instance, the axial forces in the bars. That is the recovery of derived quantities. So if we put a little bit of color, we have these two, which are mainly conceptual steps. You will see what I mean by conceptual steps. You don't actually do anything. It's something that you think of the members of the elements as separated. It's not that you have to do separating them. Then this in yellow is the actual process steps that you do, and then in orange, this is a post-process. Once you have the displacement, you can obtain anything else that you think that you may require from the problem. Okay? So we have, again, a couple of conceptual steps which you don't actually do, you think of doing. Then this is the processing, and this is the post-processing. Okay? Let's do it on an example, okay? And that will clarify all the ideas. This is a truss structure, absolutely simple. It only has 3 bars, 3 nodes, and the supports are like this. In a truss, the bars only work under axial forces. Okay? They only stretch or compress. Okay? We are going to prepare to work, and this is sort of the conceptual steps. I'm going to put here a set of global axes, x and y. Why here? Why not? I am going to call this node 1, this is going to be node 2, this is going to be node 3, and I'm going to call this bar 1, bar 2, bar 3. You see, all this is conceptual. I am going to assign lengths and mechanical properties to each bar. Okay? And I am going to assign degrees of freedom to the nodes. I'm going to say node number 1 is going to have ux1 and uy1 as degrees of freedom. Node 2 is going to have ux2 and uy2 as degrees of freedom, and the same for node 3. And I am going to also define the nodal forces associated to these degrees of freedom. So associated to this horizontal degree of freedom, I'm going to call in this fx1 and this fy2 and so on and so forth. Okay? So this is just preparing to work, but this is setting up everything I will need later on. Okay? This is the actual case that I want to solve. You can go home and solve any other. But this is the actual problem I'm going to solve. I'm going to consider this point fixed. I'm going to consider that in node 2 we have a roller. And I'm going to consider that here I have fx3 equal to 2 and fy3 equal to 1. Now, note. How many degrees of freedom does this structure have? 6. Okay? Easy counting, because it's 3 nodes, 2 degrees of freedom per node. Easy counting. So, of these 6 degrees of freedom, I have 3 which are fixed. 1, 2, and the vertical one here. Now, the other 3 are free to move. Okay? In those degrees of freedom which are free to move, I can specify applied forces. Okay? For instance, here I'm specifying 1, and here 2. And here I am specifying 0. Okay? On the other hand, in those degrees of freedom where I'm specifying the displacement, I cannot specify the force, because the force will be given a posteriori, it will be a reaction. So at this stage, I can say, the problem I have to solve is, first, find out the displacement which is free here and the 2 displacements which are free here. Second, find the corresponding reactions here and here. And third, give me the axial forces in the bars. Okay? It's okay? You will be satisfied with solving the problem this way? Good. Now, incidentally, this structure, this problem is rather straightforward, because this structure is statically determined. Okay? This means that rather than doing finite elements or anything, if I go to the first year and I take anybody and I'll say, okay, can you solve this for me? He will. Okay? Because imposing equilibrium at this node, I will find out the axial force here and here. Imposing equilibrium at global level, I will get the reactions. Okay? So this is a straightforward problem. It doesn't matter. because we are going to use exactly the same procedure to solve. This is the nice thing. We are going to follow exactly the same procedure to solve this problem, which a student from the first year in the first class should be able to solve, than to solve any other problem of the course or in the future. And that is the beauty, you see? The beauty is that, contrary to what we have been taught along the degree, where we have seen first certain kinds of structures were easy, then some others were not so easy, and so on and so forth, these are all easy. You see? We learn the procedure, and that's it. Okay? And the only questions we have to do ourselves are those questions that I have been doing here. How many degrees of freedom do we have? How many of these are fixed, and how many of these are not so fixed? But we don't have to ask ourselves, can we do this only on equilibrium? Well, it doesn't matter. In this particular case, you can. But it doesn't matter. It doesn't make any difference. Okay? Now, this is what we want to get. You see, this will sound familiar to you because this is a matrix form of Hooke's law. Okay? You remember Hooke's law for springs? We'll have a spring in a little while, but Hooke's law says that the force in a spring is proportional to the elongation, and the constant, the proportionality constant, is the stiffness. Okay, so what we want to do is to consider the structure, whatever the structure, as a huge spring, and we are to evaluate the stiffness of the spring, and we are going to call it the stiffness matrix. Okay? And then we are going to multiply the stiffness matrix by the deformations of the huge spring, the displacements, and this product will give us the forces. Now, because the structures in general are far more complicated in behavior than a single linear spring, we have to do these things that we are doing. But we know that for this particular structure we are studying, we know that the degrees of freedom are these. Okay? We know that the degrees of freedom that we have defined are, it appears here. We know that the degrees of freedom that we have defined are these 6, ordered like this. And we know that the conjugate forces, the degrees of freedom, are these. Okay, because these are 6 and these are 6, the matrix connecting the forces to the displacements or the displacement to the matrix is a 6 by 6 matrix. Okay? And we are going to call this the master stiffness matrix or the global matrix. Okay? On the other hand, we are going to build this master matrix starting from relationships like this. And this is exactly the same, but at element level. So we are going to distinguish with a little bar on top the relationships and the magnitudes at local level. Okay? Now, at local level, we have a bar, as I said at the very beginning. I have a bar with 2 nodes at the end, and each node has 2 degrees of freedom. So we have 4 degrees of freedom. We are going to see it in the next overhead. 4 degrees of freedom and 4 forces, and the elemental matrix is 4 times 4. Okay? Now let's go and see how this works. The first 2 breakdown steps, disconnection and localization. Well, there they are. Okay? We have disconnected this node, and disconnected this node. This is element number 1, element number 2, element number 3. And we have defined the local access for element number 1, element number 2, and element number 3. Okay? There are different ways of doing this, but you will guess which is the one I'm following by looking at the picture. Okay? So they are defined. Now, here is a spring. Okay? A spring has one F at this end and the opposite F force at the other end. And it is in equilibrium. Okay? And because it is not breaking, it has an elongation D. Okay? And I insist, because it's not breaking, that's compatibility for you, it has an elongation. And we know that the relationship between the F and the D is Ks. Okay? So we can write for the spring, we can write F equal Ks times D. And that's Hooke's law. Okay? So that we already know. That's linearity and elasticity for you. Now, we are going to identify our member, our generic member, with the spring. So we are going to have here a node I and a node J, and here we are going to have the degrees of freedom and the conjugate forces, and here we are going to have the degrees of freedom and the conjugate forces, and now we are going to try to identify what we know for the spring to the elemental member. And that's simple, and that's this. You see, for the stiffness, for the spring, we know that the F is Ks times D. Okay. But the elongation we can define as the horizontal displacement of the node at the right minus the displacement of the node at the left. Because we are not considering cracks. That's compatibility. Okay? And we can, by pure identification, we can identify F with Fxj, and we can identify minus F with Fxy. And that's equilibrium for you. Okay? So here, in yellow, we have linear behavior, Hooke, we have equilibrium, and we have compatibility. Okay? And that's it. Okay? That's it. We don't need anything else. And we cannot do with anything less. We have to have compatibility, we have to have equilibrium, and we have to have some relationship between the both, between the forces and the displacements. And that's elasticity. Okay? So that's the three pillars of our table. We can do with 3, we don't need more than 3, and we cannot do with less than 3. Okay? Now, the rest is a matter of putting things in a convenient way. Here, we have put things in a convenient way for the spring. Now we put it for the stiffness method. You see, we put here the local displacement, we put here the local forces, and this is the matrix relationship which relates one to the other. For instance, Fxi is equal EAL times Uxi minus EAL times Uxj. The vertical forces are 0. Okay? Now, this, which is this, is the elemental stiffness matrix in the local axis. Okay? That's it. For this element, which is very simple, it takes a very simple form. So what have we got so far? We have localized, we have considered a generic element, and we have the stiffness matrix of the element in the local coordinates. So what do we do next? We globalize. We take this element that we have somewhere on the work table, and we put it back in its place. To put it back in its place means to change this local relationship into the global system, put it back. Now, I don't want to go into details because you know the details, and anyway they are written. You can, if you have these are the global axes and these are the local axes for bar whatever, you can always express the local displacements in terms of the global ones. Okay? You only need to know which is the inclination of the bar. Now, we put that in matrix form, and in matrix form it reads like this. Okay? Compact form, it reads like this. The local displacements can be expressed in terms of the global displacements using a transformation matrix, which is this one. Okay? We can do this for the displacements, and obviously we can do this for the forces. Okay? If we do it for the forces exactly in an analogous way, we get this. Rather than writing exactly the same, we have written it the other way around. You see? Here we have written the local in terms of the global, and here we have written the global in terms of the local. Obviously, the matrix that appears here is the same matrix transposed. Transposed because in this case the transpose and the inverse is the same, because these are orthogonal matrices. Okay? Now, we know how to globalize or localize displacements and forces, which means that starting from this relationship, which is local, we can plug this here, and then we can use this, and then we can, it's a simple algebraic manipulation, then we can see that if you know the stiffness matrix in local coordinates, you can easily obtain the same elemental matrix in global coordinates by doing this transformation. And if you do it, you get it directly like this. Okay? You see, this is the axial stiffness as before, and here you have cosines and sines and sines and cosines put in this way. Okay? Which means that knowing the E, the A, the L, and the inclination of a bar, you can directly form the stiffness matrix, the local stiffness matrix. Now, let's go back to the example. Let's go back to the example. Remember, this was the example we wanted to solve. Okay? These are the lengths, these are the properties, and this is the numbering of the matrix, of the members and the nodes. So let's build the matrices according to what we have just seen. There you are. See that, for instance, bar number 1 goes from node number 1 to node number 2. And it involves the degrees of freedom and the forces of node number 1 and node number 2. So here it is. This is the relationship for element number 1, and you see that it involves the degrees of the forces and the degrees of freedom of bar number 1. Okay? And it is 4 times 4. The same with the others. Okay? Now, because this bar is horizontal, the transformation angle is 0. So this matrix looks exactly like the one we showed before. This bar is vertical, so the rotation angle is 90 degrees. So when we do the transformation, the 1 and 3rd bar will turn into the 2nd and the 4th, and vice versa. You see, the horizontal and vertical degrees of freedom will be switched. And that is what you see. You see, these zeros go here, and the 1 and the minus 1s move from the 1 and 3 to the 2nd and 4th, because they are swapped. And finally, And finally, I'm sorry again. This bar is inclined 45 degrees, so you will have the sine and the cosine multiply and square and so on, and you have this. Okay? Now, all this you probably remember, okay? Because all this is the... Now, this is the next one is the important one. The only interesting thing is the next one. So what do we do with this? What do we do with this? I mean, here we have one relationship for each bar, okay? This is like going to the shop and buying the bar, okay? You go to the shop and you ask for this bar, horizontal. You ask for this bar, vertical. And you ask for this bar, which is a diagonal. And then what? And then what? And then you have to assemble them, okay? That is the actual engineering step. You have the pieces, you have the bars, and you have to assemble them. And how do you assemble them? Well, we have two rules and only two rules. These two. Sorry. These two. So this is where the real thing goes in. We have compatibility and we have equilibrium. I told you before, and I will insist one and again. Apart from the constitutive behavior, you only have two weapons: compatibility and equilibrium. And you know when to use them. Now, compatibility, in this particular example, remember that we have already used compatibility at local level. I have said, because there are no cracks, the elongation of the spring or the bar is the difference between the displacement of one end minus the other, because there are no cracks. So I have already used part of compatibility. Now I'm going to use the rest of the compatibility, and I'm going to say the joint displacement of all the members meeting at a joint are the same. Okay? So I'm saying if this bar is meeting this bar, the node has the same displacements because of compatibility. Because if not, they would separate. That's compatibility for you. Okay? And the second is equilibrium. And you all know what equilibrium means. It means I will look at the axial forces, internal axial forces of all the bars meeting at a point, at a node, and they have to be in equilibrium among themselves and with the external forces, if any. Okay? That's equilibrium. But never forget compatibility. So how do we do that? Well, first we do something that we can do on the blackboard or on the projector, but we are not going to do in real life. But you will allow me the trick. Going one step back, you see that these matrices, all three matrices, are 4 times 4. And this matrix only applies to nodes 1 and 2, and this one to nodes 2 and 3, and this one to nodes 1 and 3. I'm going to extend them so that all of them are 6 times 6. Why I do that? Because I want to end up with a global matrix which is 6 times 6. So I want to have the liberty to be able to add it on top. Okay? Obviously, in a real program, you don't do it this way. You go and put the small matrix where it goes. Okay? Because the global matrix can be huge. So you are not going to extend all the elemental matrix into huge so that the operations are simple. You take the trouble to make the operations a little bit more, but that's not the point now. Okay? So I just extend the previous matrices. You see, I have added here zeros and zeros. I have added here zeros and zeros, and I have added here zeros and zeros. Okay? Just to have all of them the same size. Okay? So now I'm prepared to put in compatibility and equilibrium. Well, compatibility is very simple. You see, here Compatibility is very simple. That is why I said that in this method you take compatibility to start with. You see, here I have defined ux1 on bar 1. And here I have ux1 on bar 2. And here I have ux1 on bar 3. So I just drop the number of the bar. I just drop this 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 3, 3. And then you have compatibility automatically. You see? You see? I had forces in bar 1 equal to the matrix in bar 1 times the displacement in bar 1, and so on and so forth. Well, I just drop the subscript here and here and here because the displacements are all the same, and that's compatibility. You see? It's impossible to make it more straightforwardly than this. Okay? Now, there is no way you cannot have compatibility. Okay. And doing equilibrium is not that difficult either. You see? Consider node number 3. In node number 3, we have two members meeting, element number 2 and element number 3. Okay, these are by definition the positive axial force in member 2. And this is by definition the positive member force in element number 3. Okay, so this is by definition. Also by definition, principle of action and reaction, on the node, this member will make this force with the sign reverse. And also by the principle of action and reaction, this member will make on this node this force reverse. Okay? And you may have an external force. Okay? So you have to have equilibrium here on the node. So you write it, and this force, which is this force, must be equal to the addition of all the other forces, of all the members coming to the node. Okay? So you do this for all the nodes, and that's equilibrium everywhere. Okay? Let's see how it works. You see, the total force on the whole of the structure is the addition of all the forces in the three members. And the forces in the three members are the stiffness matrix of the three members times the U, which is only U, and that's Ku. So you actually have to do this, adding the three stiffness matrices. And there you are. Okay? And there you are. Notice that it is as simple as that, adding them together one on top of the other, because we have taken the precaution of expanding them. This is impossible to do in reality. Now, if you don't do that in reality, then you have to know that this 10 and this minus 10 go there, and these 5 go there, and these other numbers go somewhere else. Okay? So you have to do a little bit of pointing. Anyway, following the same rules, plus your own storage rules, to know where you have put everything, you end up with this. Okay? And that's almost there. Let's do a little bit of a recapitulation. What is this? What do we have here? We have global equilibrium. We have all the forces in the structure expressed as the multiplication of a matrix, which we have gone to this trouble to find. This is the stiffness matrix of the structure. And these are the displacement, the degrees of freedom of the structure. But here, we don't have What is missing from here? We don't have the boundary conditions, and we don't have the forces. So this is like having the structure in the box. Okay? It's like we have built the structure, it is in the box. We have to take it out of the box, we have to fix it somewhere, and then load it. Okay? Now, that's relatively easy, because this is the original problem, that is the problem that we wanted to solve. So we want to impose these three known displacement, and we have to impose these three known forces, okay, on this. Okay, the forces are very easy. We go and put the forces where they belong. And the displacements are also easy, because if we know that ux1 is 0, then we just delete the first row and the first column. The first column, why? The first column, because all the numbers in the first column are multiplied by 0. And the first row, why? Because the first row is the equation to find out the ux, but we already know that ux is 0. So if we do this, we end up with this. Well, this is the same. We end up with this. We have deleted the rows and the columns corresponding to the degrees of freedom that we already know. And we have put the forces that we already know in their places. Now, this system is not singular. This system can be solved. Okay? It's called the reduced stiffness equation, whatever. This can be solved. On the very contrary of this one, this cannot be solved. Why cannot be solved? Why it cannot be solved? The mathematical reason is that this matrix is singular. Okay? How do we know that it is singular? How do we know it is singular? If we compute the determinant, it will be 0. Easier? Easier? Look at this row. 0, 0, 0, 5, 0, minus 5 is equal to 0. So it's singular. Look at this one. 20, 10, minus 10, cancel out. Minus 10, minus 10, 20. Cancels out. Okay? So every single row and every single column, because it's symmetric, cancels out. So it's symmetric. Okay? It's singular. So it's singular. And why it is singular? Because it has to be. Because we haven't put the boundary conditions yet. So the structure, even with the loads on, is flying in the air. So how can I solve for the displacements if it is flying in the air? With the loads or without? Suppose this is the structure, okay? Suppose this is the structure. With the loads or without? Suppose it is a stretch. I can put it here, but I can put it here, or here, or here, or here, or here, or bring it home. It will be in equilibrium, it will be a stretch, but I cannot determine the displacements. To be able to determine the displacements, I have to put the boundary displacements. Then it will be fixed. Okay? And that is what I do with fixing the displacements. Now it's almost finished. Now we solve for this, and we solve the unknown displacements. Okay? Now, if we know the unknown displacement, we can plug them into the U. These are the three that we have just found, and the other 3 zeros we already knew from the beginning. Okay? And now we can make a plot of the deformed structure. Anything that we do now is post-processing the results. For instance, What about the reactions? Well, we can go back to the original equilibrium equation. Now we know all the displacements. We can make the multiplications. And here we find, you see, first row times all the displacements. This is the reaction, the X reaction here. Okay? Remember that the first row we have disregarded to get the reduced system. But it doesn't mean that it's wrong. You see, we are using it now. Now that we know the displacements. Okay? The same with the second row to get the vertical reaction here. And the same with the fourth row to get the vertical reaction here. Okay? We can also find the axial forces at each member. How do we do that? Well, we go to the U and we disregard the values of the nodes which are not at the element. So we extract U of the element. We transform to local, and then we compute the elongation, and then we compute the force. Okay? So we go back to each element, one in turn, and we compute the axial force. For instance, if we want to know the axial force here, we remember that the inclination angle is 90 degrees. So we go to here, and we extract the displacements of nodes 2 and 3, meaning that we forget about this. And we get this. There is a minus here, it's wrong. Okay? Minus is missing here. We build the T again, the transformation matrix. We multiply, you see the minus? We multiply and we get this. Okay? Now, the elongation is this minus this, this. It's a negative elongation, means it is a shortening. This is the E, A, and this is the L, and this is minus 1. This is the axial force in compression. And this is for the other two. Okay? And that's it. And that's it. End of the class.